So now we're beginning to talk about electric forces and electric fields, but because of that we have to talk about the basic nature of electric charge. So when we talk about gravity, the gravitational force, we know that two things can experience a gravitational force if they have mass. That's what gets attracted by the gravitational force. So people were studying things and realized there was a separate force that involves things that we ended up calling positive and negative charges. Okay? So you have these things in nature that can be positively charged, or negatively charged, or zero. They can have zero charge too. Okay? And so the fundamental things that we usually think about with this is we have the proton with positive charge, and we have the electron with negative charge. The electron has a mass that is much, much less than the proton's mass. And so usually when we talk about charges moving around, we talk about electrons moving around and not protons moving around, because it's more easy. It's easier to actually accelerate the electron than it is to accelerate a proton. And so the electron, E minus right here, has the fundamental unit of charge. In nature, we find out that the charge always occurs in multiples of the charge that we find on electrons. And that charge has a value of 1.602 times 10 to the minus 19th coulombs. Okay, it's a new SI unit that we have to introduce here to just talk about the amount of this thing that we call charge that we attribute to this sort of phenomenon that we give the two different separations of positive and negative. And what we know is that like charges repel, and unlike charges attract. And we're going to use that fact, an experimental fact you can check for yourself, okay, to talk about this phenomenon of the electric force and also the electric field. Okay? But first we have to start thinking about what that means and how we can actually transfer charge from things and what charges will do. So if we have something that is very good at transferring charge, we call that a conductor. Metal, mostly we're talking about. Things with salts, things with ions in them are able to actually be able to do this. Like if you put salt in water, it conducts electricity. However, other things that don't have that sort of ability end up being what we call insulators. They do not transfer charge very well. Glass would be one of them. Rubber would be another. You can't actually transfer charge. You can have a flow of charge off of them. So if you have something that can conduct, let's say we've actually we put charge onto a certain bar, we made it negative, and we bring it towards a neutral sphere that's a conductor, that therefore the charges can move around. What's going to happen? We know that like charges repel, and the electrons are the ones that are going to move around. So we bring this negatively charged rod in, and it's going to push the electrons that are nearest it away. So electrons end up moving over here on this side, which means that it looks like there's a dearth of electrons or a lack of electrons on this side. So it looks like it's positive on this side, just because there's a lack of electrons. By the way, one more thing about the universe is that charge is always conserved. You have to think about that. So there's no way for charges to move anywhere off of here, so you're still going to have a net charge of 0. Okay. So now if I were to touch this bar to this sphere, what's going to happen? These negatively charged electrons in here are going to see this space of a lack of electrons, and they're going to flow over. So what happens is that you end up with a net negative charge on this because you gain charge from this side. Okay. Now the universe, like I said, charge is constant, so the charge you lost from here equals the charge you gain here. Okay. So this would end up becoming negative. It would match the same sign of charge that was on this bar that touched it before. But that involves touching it, so you actually can have the flow of charges over. Okay. So now, let's keep this negatively charged idea, but let's connect this conductor to the ground. Okay, we're going to say that we have some wire that's connected to this and going down into the Earth. So the Earth is an infinite reservoir of electrons. Electrons will want to flow down there. So we think of it that way. And so whenever you have outlets that have a ground, that's what we're talking about with regard to this. So the electrons are free to move. So what's going to happen when you bring this charge over? Well, they're still going to separate, so that you end up with the negative charges moving that way, leaving some positive over here because the negatives had left, but the negatives have a path to go on. They're not confined by the edge of the sphere. And so they're actually going to fly through, I should say, the wire, and leave the sphere. So that you end up with an overall positive charge. This is called charge by induction. You're not actually touching it, you're just bringing it nearby. And you're letting the charges on here actually flow off. Okay? And the charges from the Earth are not going to flow up. There's no reason for them to. Okay? So, conduction involves touch. Induction does not. And conduction leaves you with your new object having the same sign of charge as what was originally there. Induction leaves you with a situation where the object has the opposite charge of what was originally there. And so we'll be talking about more of this phenomenon with what charges are and how they move, how they interact when we talk about the electric force next class.